So howdy there, Internet students. This is Mr. Hermanson. Today we're going to do lesson 1.1a. Again, just a reminder, you need to have your packet out. I've attached the packet to the class assignment, so you can just print it off from there, or maybe you already have it. Or if you don't have it yet, then at least have some blank paper that you can do your work in. So we're going to do today, we're going to learn about increasing relationships and how they look on graphs, how you write equations for them, and so on. So let's start by doing this problem here. It says choose an integer on the x-axis. So let's say I choose this one, 3. You're going to multiply that by 2 and then move your icon vertically to the value. So 3 times 2 is 6. So actually I'm just going to put a dot right there at 3, 6. Okay? And go ahead and do that for all the integers on the x-axis. So every one you're going to multiply by 2. So 4 times 2 is 8. You're going to put a dot there. Go ahead and do all those. So that graph should look like that. Now we're going to make another graph, and I'm just going to pick a different color for that. On this one, we're going to choose an integer on the x-axis like we did before. So let's say I take 3 again. And then we're going to multiply our integer by 2 and add 3. And then we're going to find where that value is on there. So basically we are plotting coordinate pairs. So if I take 3 times 2, and then I add 3, that would be 9. So at 3, I'm going to move mine up to 9 right there. At 4 times 2 is 8 plus 3 is 11. That would move that up to there. Okay, go ahead and do that for all the integer pairs on the x-axis. If you did that correctly, you should have the dots that look like that. Now we're going to answer a few questions about your graph. Okay, go ahead and pause here and fill in the answers to these 4 questions. All right, so are they both linear? That means, do they line up in a straight line? For sure, yes. Does either graph pass through the origin? Origin is the point 0, 0. Just, you might want to write that in if you forgot that. And yeah, the black one does. The black dots go through the origin, the one where we're just doing times 2. Write an equation for each graph. Well, my 2 equations are y equals 2 times x. Remember, x are the numbers on the x-axis. And y equals 2 times x plus 3. In algebra, this is what the equations would look like. And explain why the 2 graphs will never intersect. That's because they're parallel, and parallel lines never intersect. Okay? Now, one thing that I'd like you to take notice is that this line right here goes through the origin. If the line goes through the origin and it's a straight line, we call that a direct variation. We're going to talk about this some more, so don't worry about that right now. And if it does not pass through the origin, then it's not a direct variation. It can still be linear, though. Okay? All right, let's move on. And we got a problem here where Michaela is delivering pamphlets, and on Saturday she delivered 350 of those pamphlets. On Sunday she delivered 150 each hour. So she had already done some on Saturday, 350, and then she continued on Sunday delivering at a rate of 150 per hour. Okay, we're going to fill out a table that shows that. Now, important note here, this line represents just those delivered on Sunday, not including the ones on Saturday. The second row includes the ones delivered on Saturday. So let's get started by just filling in a couple of numbers here. So On Sunday, she's delivering 150 more every hour. So our hours are in the first row. So that would be 350, 300, then 450. Notice I'm increasing by 150. And the total deliveries also increased by 150. They just start at a different number, 350. And now we're going to go up by 150 there each time. Go ahead and fill in the rest of that. Now I'll get you started on this and making your graph. We have a graph all set up here, but basically we're going to make 2 lines. So you might want to pick 2 different colors, whatever. But so let's start with the Sunday delivery line. That starts at this point right here at 0, 0. So we'll do that in blue, 0, 0. Then we have a point at 0, 150. Then we have a point at 0, 300, or at 2, 300. That means 2 hours, 300. 3 hours, 450, and so on. And the second line, I'll just change my color to red there. That one is going to be the total deliveries. That one starts at 350. And then after 1 hour, it's at 500. After 2 hours, it's at 650, and so on. So go ahead and finish those 2 lines. All right, if you graph those correctly, your line should look something like that. And go ahead and fill in these 2 questions right here. What similarities do you notice? What differences do you notice? And then I'll show you what I think about that. One thing you might have said is that they're both linear. They make straight lines, and they're both going up at 150 per hour. I wrote 250 here, but I meant 150 there. And then the things you probably notice that are different is that where they start on the y-axis is actually different for each of those. Okay, now to write an equation for this, go ahead and give that a shot. They're going to, remember those equations that we wrote for the first 2 problems? One was y equals 2x and the other was y equals 2x plus 3. They're actually going to look a lot like that, just different numbers. Go ahead and give it a shot, see if you can get it. So pause and then check your answer. So for Sunday deliveries, that one just goes up by 150 per hour. You should have wrote S for Sunday deliveries equals 150 times H. And in algebra, we don't put any time symbol in there to represent multiplication. Now the total deliveries, it also goes up by 150, so it has that part the same, 150 times the number of hours, but we're going to have to add the Saturday deliveries on to complete that equation. So those are your 2 equations there. Okay, now one thing you should notice about the ratio of Sunday deliveries, you should notice that you always have the same ratio. So 150 over 1 hour, 300 over 2 hours, 450 over 3 hours, all those ratios are equal to 150 over 1 when you reduce them. Now, if there is, if we look at the total deliveries, we start with over 1, we had 500, and then we had 650 at 2 hours, and then we had 800 at 3 hours. Now you can see that these are not equal to each other. There is no constant ratio. Well, one way you can tell that there's a direct variation, and we can go back on the last backup page and we have a spot to write this. Back 2 pages. Direct variation is a relationship with a constant ratio in the variables. And we also saw that the direct variation starts at 0, 0, the origin, and is linear. Okay, directly proportional means that what we just said about the constant ratio, that you always get the same ratio in the variables, that they're proportional. Okay, let's go back to the problem now. And we'll check out a new problem and see what happens. Go ahead and answer number 8 through 10 to the best of your ability. And we'll talk about those. All right. Explain why the graph for Sunday deliveries passes through the origin. Well, that's because at 0 hours, there were 0 papers delivered on Sunday. And why the graph for the total number of deliveries does not pass through the origin, that's because at 0 hours, we already had 350 delivered. Explain why the graphs will never intersect. That's because they're both going up by the same amount per hour, same rate. Okay, the 150 is the rate of delivery per hour. If you change that to 100, you'd have less steep line. It wouldn't be going up as fast. And if you changed it to 250, it would be more steep. Why does it have to pass through the origin? If it doesn't, then it won't be proportional. And to be a direct variation, you must be proportional. All right, that's the lesson for today. You can go ahead and do the homework and then make sure you put the selected answers on the Google form. All right, good luck with that. We'll talk to you soon.